Thank you very much, John, for the very nice introduction. And as you see, my accent is not American, even though I was born American. So I was only 4 years when I moved to Finland, so that's why I don't speak fluent or at least perfect American English. Okay, so from the title page you see that my home institute is actually electrical engineering, and however I'm a theoretical physicist, and in electrical engineering everything is labs, so even theoretical physics is lab. At the same time I do have an appointment also at physics, so if you are a physics student and want to be affiliated with physics, you can try to go to that route. Okay, so I'm doing mostly many-body physics combined with quantum optics. And today I'm kind of trying to introduce you to the general field and where you can use different theoretical approaches to approach interesting questions. And my general theme of my research is to understand not single-body many-body physics, but multi-body quantum physics. So in your Hamiltonian, you have then not 2, 3, but really thousands of particles. And you all know that when you are trying to do quantum physics, you usually try to isolate the effect to as simple as possible. However, in a many-body physics, the same thing would be that you isolate the phenomena and try to then propagate it so that you can detect it, control it, and so on. So the dream is to kind of figure out real quantum phenomena that collectively can be seen from the real world. So if you can do it, then of course your access to quantum world will be much better than if you are just probing one single atom, for example. So I think an easy example is the Bose-Einstein condensate. So everybody was very excited because if you have 10,000 atoms in the same state, it sort of amplifies all your quantum effects. If you take the same analog, so you try to do the same thing in all kinds of devices, so in semiconductors, molecules, biological systems, and so on. And if you take an engineering point of view, you can just start thinking in which format is the information encoded in a many-body system. So what is the bit of quantum information? And in a many-body world, we are trying to talk about wave functions, and you have many of them. So a wave function will have a description of all possible states within the many-body system. And if you have n particles, and if and let's say they are identical one way or another, and each of the particles could be categorized to, let's say, 1,000 states or 1,000 elements. If you have now n such particles, the information content is the number of elements to the power of n. And it doesn't take you long to realize that this amount of information is simply too difficult to handle, so it grows without your numerical capabilities, so you cannot really handle it. And let's say that you are nonetheless clever and you are able to encode it in a very neat way so that you can, let's say, compress the information to some simple elements. There is actually a fundamental thing that will make it again difficult, and the thing is that when we have many-body systems, we don't want them to be isolated. You want to have interactions, otherwise there is no interesting things happening in your many-body system. So, the interactions, once you switch them on, the information you had initially, that starts to be scrambled, or one way of saying they become entangled. So, and you see it if you do theoretical analysis of these problems, you see that you get a hierarchy problem, for example, or you create correlations that you eventually cannot handle. So, in general, many-body systems with interactions, so it can be, let's say, electrons interacting with electrons, or you take electrons interacting with quantized light field, then you are talking about quantum optics. They will give you correlation problems or scrambling problem. And let's say, without specifying in any more detail, so you can almost, if you really want to find exact solution for many-body problem, you can so and so do it until 3-body problem. So if you go to 4-body or higher, in a general level, it doesn't really work out. So obviously we have to come up with another alternative way to do it. And let's think about what are the possibilities. So let's take an example measurement of a quantum state. So Born's theorem states us that if you measure a quantum system, it will give you randomly outputs that follow a quantum mechanical probability distribution. And here is one very schematic way of measuring, let's say, particle position, and you have then histogrammed them, and the histogram is then the red line. And now the Born's law says that if you make infinitely many measurements, that red line should match exactly the quantum mechanical distribution. And obviously that task is somewhat difficult. However, we can approach it differently and identify the quantum mechanical distribution by looking at simpler quantities. And the one way of doing it is that take this red curve, compute its mean and variance. That will already quantify a little bit about what are your quantum fluctuations in the system. And you can do it in a more general level by introducing a set of cumulants, which would be higher order moments, so x to the c, and then you remove all the factorizations and they define your cumulants. And the higher in cumulants you may go, the more detailed information you have from your quantum mechanical distribution. And these ones come statistically accurate relatively fast, so it's clear that going this cumulant path identifies your distribution faster than really trying to make this converge to fully smooth curve. So, and in principle, if you would know all the cumulants, you would have perfect information. However, usually the lowest order cumulants tell you most of the information you are interested in anyway, so that might be a good idea also in many-body world. So in many-body world, as I started, we usually don't start with wave functions. Instead, theoretically, we introduce field operators and their expectation values. And now, following the idea of the cumulants, you can factorize these expectation values to smaller order expectation values. So here this is a C-particle expectation value. So you remove all the expectation values in a systematic way, starting from 1 to C minus 1 particle expectation values, and you will get kind of a cumulant, but in this connection they are called clusters. And just terminology, so the lowest order cluster is called singlet, second order cluster would be doublet, triplet, quadruplet, and so on. And what do they tell us? So in a many-body system, if you have a cluster, that means that you have a collection of particles that try to stick together. So they are sort of connected by interactions, for example. And in a semiconductor, we would name these different, or they would identify, for example, different quasi-particles. So within a solid, a certain collection of electrons can make a Cooper pair, electron and hole can make an exciton, and so on. So how can you use this cluster information? So I will sketch it a little bit. So usually you start from a generic Hamiltonian. You would have the free particles, which is somewhat treatable. Then you add your interactions, and typically in these problems we are talking about electronic interactions and interactions with the quantum optical light fields. And in a solid, of course, you also need lattice vibrations, so phonon interactions. And you can study this in connection of semiconductors, where you start with the one valence band and one conduction band. You create excitations, you excite electrons to the conduction band, leave behind holes, and in this connection you can do these excitations via laser light. And it happens to be so that if you excite with a classical laser light, you initially create plasma, and that one is a somewhat more general thing. It includes possibility to have coherencies, coherent polarization. And it happens to be so that these are initially created, and the higher order clusters build up via the interactions sequentially. And this dynamics is strict, and you can really solve exact dynamics of the clusters, and they have roughly this form. So C-particle cluster couples to C-particle clusters, but also all the lower order clusters. And then here is this hierarchical coupling, and this is the difficult part because that in principle will generate as the infinite hierarchy, which is not solvable. However, now, since if the evolution is sequential, so after an excitation, there is a very natural way of truncating. So let's say that you are in a situation where the triplets have not been generated. So that means that if you have here C is equal to 2, then you can neglect this three-body correlation altogether, since they are not yet there. And you can truncate exactly the dynamics until the next order is generated. So with a cluster, that's the idea of the cluster expansion. You classify the clusters and follow the sequential build-up until the point that the next level has not yet formed. And until that next body has formed, you can follow the quasi-particle formation dynamics and so on. And it's actually completely non-perturbative, so that's a nice thing. And Clustronics, that was in my title, so now I can introduce what it is. So essentially what we try to do is that we try to follow a given cluster, how it is formed, and we try to control it via quantum optical and many-body interactions. Okay, I want to prove it to you that Clustronics is sequential, and here's the proof. So that's very easy. Okay, it's not a proof. Proof, it's actually more appealing to your intuition. So it's actually very natural. So if you think of a Big Bang, first it generated simple elements. So I think here are some quarks. It took some while to form atoms. It took even longer time to form molecules, and then some more difficult, complicated entities later. So the sequential buildup is very natural in these environments. So yes, the cluster sequential buildup of clusters does make sense. So if you really want to have a technical proof, we could go through all of these terms. However, I'm not going to go through it. I just want to show you roughly how the equations look like. So here is a triplet dynamics in Bose-Einstein condensates and a couple of terms. So here are the terms that will generate the triplets. And essentially, lower order clusters scatter in and out, and in this in and out scattering process, you can generate it. And once they are generated, there is an important term here. So all the clusters become coupled among each other, and these give, for example, a binding of molecular binding and these kind of things. So, and our equations are essentially these kind of things. So you have nonlinear sources creating the clusters, and then you have this kind of integral part that takes care of it, that it is valid also in a non-perturbative limit. So even when the T grows, it will feed back so that it alters the presence of the cluster, will alter cluster itself back self-consistently. Okay, so that's roughly the bulk of the theory part. So let's start thinking how that connects to real world. And I'm going through about 4 different examples and how these ideas then give us some new insights how physics work in different many-body situations. I will first talk about quantum optical spectroscopy. Then I will talk about how you can really hurl electrons to move really fast in a solid. Then you also talk about collisions between quasi-particles, and on the last, I will not go completely away from solids to atomic Bose-Einstein condensates and show that the same approach works extremely well also in that context. So quantum optics work was done together with Stephen Cundiff's group. He did all the experimental things, what I'm going to show you, and of course my group was concentrating on the theory part. So the idea of the quantum optical spectroscopy we conceived more than 10 years ago. We were guided by the question, so okay, we have quantum optical light fields, how that will influence the excitations in semiconductor. So we know, of course, that light influences semiconductor that way that you absorb photons, it creates you the excitations. So it creates you the electron, so it moves your electron excites your electron from valence to conduction band are many of them leaving out many holes. And it basically creates you the interacting many-body system. However, is there a deeper layer on that? So is there a difference whether or not your light is classical or if it has true photon correlation? And I already showed to you that if we take classical laser, that one is, so if you think in terms of photons, your photons are uncorrelated. So if you absorb one photon, the next photon will behave the same way. So there is, for example, no anti-bunching or bunching, and so on. And you can do also cluster expansion analysis of the quantized form of the classical light, and you realize quite easily that these are entirely defined by singlet photons, so essentially the amplitude of the light field. So, and now if we do classical spectroscopy, that one is guided by the sequential buildup. So the excitons build up at some time, triplets by excitons, so exciton molecules sometime later. And obviously these are the interesting clusters which we are interested in. But now you see that this is somewhat separated. So excitation is separated from the interesting bodies. So there is a kind of a access problem. So yes, you can analyze them, but it will be difficult because there is so much dynamics in between, and you know that if there's many possibilities in between something what you want, quite often you wander to ranges which you don't want, and that will, for example, make it difficult to detect higher order clusters in your signal. Okay, so then we ask really the question, so what if we didn't use classical light but had a light field with 2 photon, 3 photon, 4 photon or higher order clusters or correlations. And it turns out that these correlations, if you analyze it carefully, will be transformed as such directly to your system. So if you have 2 photon correlations, it will create you correlated electron hole pairs which are doublets. If you have 3 photon correlations, it will create you correlated triplets and so on. So quantum spectroscopy could have direct access to these clusters. So that's the idea of the quantum spectroscopy. So it works both in the excitation direction and in the detection direction. So if you would have a quadruplet, it would, you could see it in the 4 photon correlations. And we wanted to test this in a simplest possible and most well-known semiconductor experiment. We took gallium arsenide, quantum wells, high quality such, and made a pump probe. And what I'm following here is a probe absorption as function of pump. And the pump is the one which creates us now the clusters. And if you do classical spectroscopy, the absorption spectrum looks like this. So the red areas are where the absorption is strong, and white where it's weak. So, and now I'm actually following it a very unusual way, looking at stuff close to bi-exciton resonance. And this axis, x-axis, is the number of photons in my pump field. Probe field is all the time the same. So it basically just measures which frequencies are absorbed by the system after the excitation. So in this particular case, in the lower excitation range, we do see nice bi-excitonic resonance here. Then when you grow, something might happen, but it's somewhat blurry, and maybe here is something unusual happening, some bifurcation or something. However, you see easily that it's not very, it's not easy to distinguish what is going on. So after some long work, we figured out how to convert or actually project this one, the information related to 3 photon excitations. And the spectrum changed dramatically. So the shaded areas show you the spectra, real spectra, and then the red areas show where the absorptions are strong. What you do see is that you see at low densities, we do see the bi-exciton, and then all of a sudden a jump, quantized jump, another jump, another jump. So there is a clear quantized structure. And of course, like always, if you see energetic quantized structure, you are associating these with new quasi-particles. And of course, we started then studying them very strongly to figure out what's going on, especially since we know that these are quasi-particles that are stronger bound than excitonic molecules. So they are must have more than 3 electron hole pairs bound together, and that's essentially what it says when we excite with a 3 photon correlated light. And yes, we analyzed it again with cluster expansion. The thing is that you can write down exact Hamiltonian for this one, and you can figure out the energy as function of two-body correlations. And the nice thing, so you all know density functional theory, you write down the energy functional and function of density. However, the correlation functionals are not exactly known, which gives some uncertainty how it is. If you do it with clusters, the energy functional is exact. That sounds really dramatic. However, it actually only states that we can link for postulated correlation what is the corresponding energy. We don't know if that correlation exists. However, it gives us a possibility to play around whether or not we can find energetic states below the biexcitons. And we could find configurations, and the easiest configuration was to assume liquid states. So electrons sitting here, and hole sitting in the center, and electrons organized in rings, not in a molecular binding way, but really as a liquid rings. So this could give us energy lowering below the biexciton. And of course, then you scratch your head, where does the quantization come from? So that comes, of course, from the particle in the box problem. So, and in this situation, we are now talking about actually relatively high density situation. So we can have a situation that we have a plasma surrounding the liquid, and the plasma would create us a potential wall around our liquid, and in this case, actually this wall will quantize the energies. So, and the quantization energies then tell us how many electron hole pairs we have in this liquid phase, so 3, 4, 5, and so on. And we tested it, so with these functionals, we figured out the energy ranges which are given by these, and they smacked on, corresponded with these energy transitions. So yes, these are these small electron hole droplets, which we call them dropletons. Okay, so that's one part. So I would then promise to tell next story. How are they clusters useful looking at strong field excitations? And this work is done together with Rupert Huber's group in Regensburg. And the dream is to do light wave electronics. So you take a semiconductor slab here, excite it with very strong field, so it not only creates you the electron hole pairs, but once it has created it, the field is so strong that it moves it to a desired position, so something like here. So, and if this is so strong that it can do it within a cycle or sub-cycle of your field, we are talking about possibilities to coherently move electrons within few femtoseconds. So it's super fast dynamics, coherent dynamics, and it will remain coherent because the movement is faster than scattering time. So if you are able to do it within 5 femtoseconds, it wins all the scattering events. And that is a very interesting range. It could give us a new possibility to coherent light wave electronics. Similar things have been, of course, thought in atomic and molecular optics for a long time. So you take very strong field, take your atomic system, you can excite from ground state, ionize your electron, move outside the ion core, accelerate, bring it back, and when it comes back, it will collide with the ion and emit a light, and that's called high harmonics, and it has been known 20 plus years, maybe 30 years, you can get these harmonics, and you get really high orders nowadays. So here, over 100 order. One particular thing what you would should point out, that the harmonics are typically always odd-ordered if in a simple atomic systems. Something happened 6-7 years ago because the same concept started working also in solids. So we got high harmonic generation, so Louis de Mauro's and David Reese's groups could demonstrate that, and here this is high harmonic spectrum coming out of a semiconductor, and they did see also odd-ordered ones. Of course, we can then ask whether or not there are some unique aspects for semiconductors, and we started studying it with gallium selenide and using very strong fields of the order of 100 megavolt per centimeter. And now if you think how strong it is, so the typical length scale in a crystal is few angstroms, so this would be already greater than 1 electron volt per angstrom. So these are basically tilting your potential surfaces really, really badly. So obviously they will move your electrons. They can easily rip out the electron from around an ion and move it around very fast. So gallium selenide has this kind of band structure. Now we are talking about not resonant fields, but here 30 terahertz fields, and the gap is 2 electron volt. And in order to cross the gap, we would actually need 16 terahertz photons. But the point is that these are very strong fields. So in principle, what do you, again, in a clustronic sense, you will initially create the simplest of clusters, which would be polarizations and densities. So polarization essentially is the transition amplitude from conduction to valence band. The populations, electronic populations, would be then the populations in the different conduction bands. And of course, you can also ask the whole populations in the different bands. And these will form so-called semiconductor Bloch equations. And we then did the calculations at that level. So we, of course, started with the simplest of clusters, so only singlets. And we didn't need the full spaghetti. We needed 5 bands to do that. Here's the experiment. So that's the frequency of the emission. That's the intensity of the emission. Shaded area is the experiment. Dashed line are the computations. And you do see lots and lots of harmonics. New feature is that we see actually both even and odd harmonics. That was somewhat puzzling. I will come back to it, why it is so in this particular solid. And the thing is that it is even more puzzling when we look at the time emission of the high harmonics. So not look the emission in time domain and match it with the driving field. So that's now the field that drives the solid, and here is when the emission comes. Left is the experiment, right is the theory. So what you recognize is that emission comes when the field is very strong. So that's of course natural. However, now if the field is strong but negative, there is a strong suppression. So it's a unipolar fixed to the positive crests of the field, and negative crests, it doesn't emit at all. And we did see the same in the computations. So it is somewhat puzzling why that happened, because if you think about it, nature should be symmetric. It shouldn't actually pay attention to whether or not you have a positive or negative direction, especially when you look at the band structures. They are symmetric, symmetric looking at least. So we started looking at the system a little bit more deeper, and you can understand this one when you look at dynamics going on in 3 bands. What happens then? Now I have to stress that I'm now looking at one process at a time. With these strongly driven systems, all of them are happening simultaneously. So in the end, I will add them up and come up with a conclusion. Okay, so this is the initial situation. So 2 valence bands. Now you come with a strong field, and it can obviously move electrons from valence band to conduction band and then accelerate in the bands. So that's what you expect. And if you figure out the polarization dependence, which actually defines also so that's the optical polarization generated, it will scale in, if you look at the equations with all the odd orders. And these would explain the odd harmonics in the emission. So that's somewhat natural. However, you can also make transitions once this higher valence band empties. You can make transitions from the lower innermost valence band to the central valence band. So that's also possible. And this one is also odd parity, so that wouldn't explain the even harmonics. However, once you are in this situation, things get interesting, because if you are sitting here, you can go the usual way so as depicted before, and this would be odd proportion or the odd parity in terms of the field. However, the electron can also go down and then up in 2 steps. And both steps are odd. However, since it's a 2-step, you have to make a product out of it, and the total polarization has an even parity. So it's case all even powers in E, and that actually explains the even harmonics. But it also introduces us to understanding what's going on in this temporal domain. The thing is that if you have possibilities to have direct path and this 2-step path, and they are going on simultaneously in a coherent way, you have a superposition. You have to add them up as an amplitudes, and then you have a possibility for constructive or destructive interference. So if the positive field crest will give you constructive interference, you flip the sign to get the negative thing, only the odd part changes its sign, and then these add up destructively and will suppress the emission. And we can test that relatively easily in the computations by switching gradually off this 2-step process, so this even parity process. One means that parity is fully on, 0, it's a 2-step process is off. Bright colors when the emission is coming. The upper frame shows you the field. So when both paths are in, you get only positive crest emission, and if you have only the direct transition, you get emission at every peak. So yes, so there is a quantum interference between these 2 paths. So you can even do crystallography. So in gallium selenide is a hexagonal lattice, and all these studies were done such that the terahertz field was in the bond direction, and you see that there is a broken inversion symmetry, and those of you who know it, having even harmonics is related to broken inversion symmetry, so you can also see it from here that yes, maybe there is a possibility to get even harmonics. However, you can take an excitation that is kind of in between the bonds, and you can break it vectorially this into 2 parts that are both along the bonds. And within this bond, obviously, the odd polarization will point to the same direction as the field component, and so in the others. And if you add them up, the odd parity should align with the terahertz field. Now, the even harmonics, if the constructive arm is here, it's aligned in this bond, they are aligned, so even and odd harmonics are aligned constructively. However, you see that the direction is sort of flipped, mirror imaged here, so in the other end it must be destructive in the opposite direction. And if you vectorially add them together, the even harmonics should be perpendicular to the odd harmonics. And in experiment, that's exactly what happened. So in this particular case, you get bursts at every crest. However, you get them perpendicular along the terahertz field and perpendicular. And if you spectrally resolve, even and odd harmonics are perpendicularly polarized. So let's go to the quasi-particle collider. So here the situation is such that we come with an optical pulse, create the quasi-particles, and here we create actually coherent excitons, and then come with a terahertz pulse, and the terahertz pulse then accelerates the quasi-particles. And this was done 2012, and without the terahertz field you would get excitonic absorption line here in the middle, and then the terahertz pulse, because of the acceleration, so it will actually break apart the exciton, accelerate the electron and hole, bring them back together and collide, like in the high harmonic generation arguments in atoms, and it will give you the side bands. So that was done with a free electron laser. We did it now with a pulsed excitation. And so we first, with 10 femtosecond pulse, create coherent electron hole pairs, 100 femtosecond terahertz pulse, accelerate and decelerate them, and then follow when the emission is coming out. And this is really analogous. This is actually more analogous to atomic high harmonic generation than solid state high harmonic generation. So the point is that polarization will have finite lifetime. So there will be then good times and bad times to do it. So if you create your coherence at this time and your coherent electron hole pairs die at that point, you only deaccelerate them and they never come back, so they don't give you a strong emission. However, if you create them in a good time, you first accelerate until the field is positive and then decelerate when they are negative, it brings it back, and then they recollide and emit lots of light. So there are good and bad times getting these quasi-particle collisions. And this can be easily tested. So that's a terahertz field, and this is the time delay. And yes, there are good times, large emission, bad time, good time, and so on. And we got the same structure in the experiment, and the nice thing is that now there is a delay between the field creation and then the emission, so there is a clearly kind of a collision, recollision, accelerator and collision sequence going on. One can take it one step further. Here, the previous ones was in tungsten diselenide bulk. Nowadays it's very popular to do this transition metal dechalcogenide monolayer stuff. They are semiconductors, and one interesting aspect is that you can have multiple valleys, so K and K prime valleys, so they are hexagonal lattices. They have two almost identical lattice sites, however they are separated by spin, and you can also selectively excite one K valley or K prime valley by having circularly polarized light. Now in the valleytronics, we could try this situation that you excite here in the K valley, and then with a very strong field, move the electron from K to K prime valley, and that should flip the polarization of your field. And this is what we get. So this is experiment, so that's now the polarization pattern of the excitation. You see it's circularly polarized, so it's in a linear way it's same in all directions. And now harmonic sidebands, the different harmonic sidebands, if you look at their polarization, they come linear, or more linear, or actually elliptical. And the computations, you get it the same. So obviously, we have managed to change the circular polarization of the excitation to something else, and that is a strong hint that something has been moving. And in computations, we can verify this. So we first excited the K state, and within about 5 femtoseconds, you move lots of electrons from K to K prime. And all this is possible because we are doing it so fast. So if you do it slower, you are hindered by scattering. Okay, so that's all what I had to say about semiconductors and how the clusters help you to understand what's going on. So I would, last part, I will quickly go through BEC investigation. And I think I mentioned that BECs are super interesting from a many-body sense because I think they are more or less the prime example where you can make macroscopic or quantum effects. So the BEC sort of magnifies the quantum effect of a single atom and so on. And I will show later that you can see it with your naked eye that yes, this is a quantum matter. It's not a pure particle what you are seeing. However, most of the BEC studies are done so that the atoms are very, very weakly interacting. So the point is that you want to have them condense as easily as possible. The interaction will make it, the Bose-Einstein condensation, just harder. However, a couple of years ago, Eric Cornell's and Debbie Jin's groups managed to do that so that you start with a situation that you have very weakly interacting system. They actually use Feshbach resonances. You switch magnetic field very quickly, and what it does, it essentially changes the influence of scattering length, so how far apart particles feel each other from very tiny to huge, actually essentially infinite, within almost no time, at least in the time scale of the typical reactions. And the original thinking was that that should completely kill the Bose-Einstein condensate. However, so here is the momentum, or actually wave vector, and here is sort of an occupation. This peak here is the Bose-Einstein condensate. Because of the finite resolution, it's not a delta peak, it's actually has some width. So initially it's the black line in the logarithmic scale, that's the same data. You see that it's really concentrated highly there. However, once at time zero, when you switch on the interaction, lots of stuff starts to be kicked out of the condensate to these non-condensate atoms. So that process is called quantum depletion. And roughly within 100 microseconds, it goes to steady state where there is a coexisting condensate and non-condensate states. And the problem here, at least at that time, was that there is no real theory that you can work on it, because most of the atomic systems calculations are based on Gross-Pitayevsky equations, which are perturbative in interaction strengths. So since here the interaction is infinitely strong, you cannot do perturbation theory. However, cluster expansion works very well in these contexts, because that's exactly what we are dealing with. In solids, we don't make perturbative things. However, it took some while to convert the atomic language to semiconductors. So if you really want to have some fun, have a look at this longish paper. It's quite nice. The thing is, lesson what we learned from this one was that when you have the Bose-Einstein condensate, it kicks the atoms to non-condensate states, and you create here clusters in the many-body system. And the clusters, again, in the non-condensate part, are created sequentially. You have to remember that this one is infinitely correlated state. However, the non-condensate, so quantum depletion, that process is sequential, and that's exactly where we can tap on with the cluster expansion. So we can do a non-perturbative cluster expansion, and instead of semiconductor Bloch equations, we get hyperbolic Bloch equations. And they have mathematically similar looking things, but the geometrical structure is different. Simply because other one is dealing with fermions, other one is with bosons. Okay, and let's look at how well the theory works with the experiments. So here are distributions after the quench. You go from weak to high interactions. The dots are the experiments. Everything is done quantitatively in the same absolute units, and the shaded areas are computations. So you see that the cluster expansion analysis of this one really explains everything quantitatively. So, and we also figured out that within this particular experiment, a steady state is reached in about 100 microseconds. Then something, I promise that you can see something with your naked eye, and this is one of the nicest experiments I know. So Ketteler group already 20 years ago took two BECs.
one not too far from here. He was born in Holland, Michigan, and spent some of his childhood in Ohio and some of it in Montreal. But he grew up in Finland and did his undergraduate work and his graduate work there. And he did some postdoctoral work in Germany at Philipps University, Marburg, and some more postdoctoral work in Stockholm.